let's pull back the curtain on the incredible, invisible engineering that keeps our modern world moving. When you step onto a train, it's so easy to just see a metal tube on tracks. But beneath the surface, a railway operates much like a giant living organism. It's got a subconscious reflex system, a conscious brain, and a complex nervous system spanning hundreds of miles. Let's get into it.
First off, we need to redefine what a railway actually is. It's definitely not just a collection of steel tracks and electric trains. It's a highly unified system. Think of it as the perfect integration of people, your drivers, signalers, and maintainers, products, meaning all that technological infrastructure, and processes, the incredibly strict operational rules. When these three elements, people, products, and processes, work in perfect harmony, that's what provides the safe and reliable service we absolutely depend on.
In this explainer, we're going to break down the anatomy of this system step by step. We'll look at the unified system itself, the safety layer known as interlocking, how we keep trains separated, preventing errors with train protection, automating the network, and finally, the railway's nervous system, telecoms. All right, part one, the unified system, balancing speed and safety. So what's the ultimate challenge here? The primary goal is moving massive numbers of people and goods efficiently and right on time, without ever compromising absolute safety. Think about the tension there for a second. If you only cared about safety, well, you'd never let a single train leave the station. But if you only cared about speed and capacity, total chaos. The real magic of railway engineering is threading that needle, achieving massive traffic throughput while maintaining total freedom from unacceptable risk. Moving on to part two, the safety layer, interlocking. To understand why interlocking is so absolutely crucial, just picture a massive, complex web of converging trackwork. You've got trains weighing thousands of tons hurtling through these junctions at high speeds. The catastrophic potential if conflicting routes were accidentally authorized is terrifying. You literally cannot rely on a human operator to flawlessly remember which switch is turned which way every single second of the day. And that is exactly where interlocking steps in. It acts as the ultimate, unyielding safety layer. Before any train is authorized to move an inch, the interlocking system ensures the physical points on the track are correctly set and firmly locked. It proves the track ahead is entirely clear of other trains, and it guarantees no conflicting routes have been authorized. But here's the kicker. All of these safe states are mutually dependent. If even a single one of these conditions fails, the whole system safely locks down. We're talking about the highest possible safety integrity levels here, meaning an unsafe failure is incredibly rare. Next up, part three. Keeping distance, train separation. Traditionally, railways use a method called fixed block working. Imagine dividing a track into static, physical boxes. The golden rule? Only one train is allowed in a box at any given time. Simple, right? It works out great, but it really caps your maximum capacity. So, to meet modern mass transit demands, engineers brought in moving block technology. Instead of static boxes, a moving block is a dynamic, constantly calculated safe zone that moves right along with the train itself. When you compare the two methods, the power of this concept is obvious. A fixed block requires a massive static footprint, but a moving block calculates real-time braking distances based on the train's exact speed, shrinking that required safe zone to its absolute minimum. This allows trains to safely run significantly closer together. For a busy city metro system, this tech is literally the difference between running 25 trains an hour and squeezing in 36 trains an hour. It's a massive upgrade. Part 4. Preventing errors, train protection. Now, what happens if a driver makes a mistake? Say they fail to brake in time and pass a red signal, what the industry calls a SPAD, or signal passed at danger. Well, the train protection system immediately steps in. And this isn't just a polite dashboard warning. A highly distinctive, blaring alarm triggers for the signaler. Simultaneously, the protection system literally takes control away from the driver and automatically slams on the train's emergency brakes. Finally, it automatically drops nearby signals to danger, throwing a protective shield around the entire area. It's a rapid, automated, and totally unforgiving response to mitigate danger. Today, that protective safety envelope is often brought right inside the driver's cab. Instead of peering out the window trying to spot colored lights flashing by, the driver is continuously fed data on a screen. The system calculates the current safe speed, the target speed, and the exact distance they have left to move. It's essentially a continuous, high-speed conversation between the train and the track, ensuring the train never, ever operates outside its safe parameters. Part 5. Automating the network. In a modern control center, human operators just can't manually route hundreds of trains a day. It's too much. So they rely on systems like automatic route setting, or ARS. ARS is kind of like a master chess player. It tracks the location of every single train, consults the digital daily timetable, and autonomously sets the routes well in advance, so drivers ideally always see green lights. It'll even calculate priorities if things are running late. But remember this critical rule. ARS can request whatever it wants, but it can never override the safety interlocking. The interlocking always has the final say.
Finally, Part 6, the nervous system, telecoms.
Telecommunications form the absolute invisible backbone of the entire railway. First, they give us operational connectivity, those vital voice and data links between signalers and drivers. Second, they support crucial safety services, like the railway emergency call on the GSM-R network, which can instantly stop all trains in a designated area. And third, they act as the system bearers. These are the data transmission paths that let the interlocking talk to the signals, the automation talk to the trains, and the SCADA systems ensure the trains actually have power. Without this telecom's nervous system, the whole railway is completely paralyzed. So, the big takeaway from this explainer is that a railway is so much more than just a train on a track. It's a breathtakingly complex, unified machine where human operators, incredibly strict rules, and brilliant technology perfectly integrate. Next time you're looking out the window of a speeding train, ask yourself, just how many invisible layers of safety, automation, and communication are silently working together to guide your journey?